So this last section here, this is the one, this is the hardest one. This is the one that you need to pay the most attention to. This is going to be the hardest section. So, conservation of energy. Where have you heard the law of conservation? What was it about? Energy. So what was the law of conservation of energy? What did that tell you about? So energy is conserved. You cannot create or destroy energy. Conservation of momentum, very similar. Recall Newton's third law. So every action force, there's an equal and opposite reaction force. Equal in magnitude, opposite in direction. So we're going to use this very explicitly in this section. So if I've got two objects that are hitting each other, if they have equal and opposite forces, and they're both in the, they have the same amount of time that they're in contact, these are going to be equal and opposite because time is the same. F net is the same, just one is positive, one is negative. So therefore, your impulse, or your change in momentum, is going to be the same for both objects. So in a collision, two objects experience the same impulse, just in the opposite direction. Or it doesn't need to be two things that bounce off like this. It could be one stationary and moving like this. It could be many different things, but they'll experience the same impulse. So, let's imagine something like this. You'll see lots of times they use pool or billiards in these examples. So we've got a cue ball. It is traveling with some momentum. So this has some momentum. What does it tell us? It tells us the speed and the direction, and it's hitting the 8 ball. If the cue ball comes to a stop, we want to know what is the change in momentum on the cue ball. And how about the 8 ball? So essentially what's happening is this ball is hitting this one. It transfers all of its momentum, and this one continues. So what we can first do is figure out what's the momentum on the cue ball. Or what is it asking for? What's the change in momentum? So let's look at impulse. Actually, you have the equations for this. Let's just do it the other way. M delta V. Do we have the mass? Nope. Yeah, this is what I had to do, change in momentum. That's what I thought. Momentum final minus momentum initial. What is the cue ball's final momentum? 0, because it comes to a stop. So this is 0. So therefore, my change in momentum is negative. Initial momentum, we have that already. So its change in momentum is negative 5 kilogram meters per second. We can do the same thing for the 8 ball. Now the thing is, we're not told anything about the momentum, but what do we know about these two objects' change in momentum? They must be equal and opposite. So if this is the change in momentum of the cue ball, what's going to be the change in momentum of the 8 ball? Positive 5 kilogram meters per second. So it's equal and it's opposite. So the two objects in this case, if we're just looking specifically at just the cue ball and just the 8 ball, they both experience the same impulse, just one's positive, one's negative. Row 8, the momentum of the 8 ball. The other one's momentum of the cue ball. Questions with this? Yeah? Just like I have here is fine. So I showed how I got into one and then doing this way. If you wanted to, you could say that change in momentum of the 8 ball is equal to negative change in the cue ball if you want to show it explicitly. But if you did this, that's fine. Any other questions with this one? So let's try this. We've got a clown stuck on a frictionless ice. In order to move, he's going to throw his clown shoe. We want to know the clown's momentum before and after he throws the shoe. So hopefully you can picture this. You got the clown stuck in the middle of the ice. In order to move, he throws his shoe. So initially, if we look at the clown before he throws his shoe, what is his momentum? 0. Why is it 0? He's stuck. If you're stuck, that implies you're not moving. So before, he has a 0 initial momentum. Afterwards, we're told that the shoe has a momentum going this way of 80. So therefore, what does the clown's momentum have to be? It also has to be 80. Now, you don't experience this. If you were sitting here and you wanted to throw your shoe at someone, you would not fly backwards. It's the same kind of ridiculous notion if someone shoots a gun in a movie and they fly backwards, it doesn't actually happen. So, since they both have an initial momentum of 0, both the shoe and the person, this object is going to have 80 newton seconds going to the right, so therefore his momentum has to be 80 newtons per second west, since you're told direction. So again, equal but opposite. Good with this? Which part doesn't make sense? So if we were to look at the change in momentum, so let's look change in momentum of the shoe. So momentum final minus momentum initial. Initially, it's at 0. So the change in momentum of the shoe is 80. And it's positive because it's moving east. The change in momentum of the clown is the same equation, except the momentum here is 0 initially, same thing. The change in momentum has got to be negative 80. So therefore, his final momentum has to be negative 80, meaning to the west. So that's where that comes from. So again, just to show what this is, the change in momentum of the shoe is equal to negative change in momentum of the clown. And that's still the concept that we've got here. Any other questions with that one? No, I've got people fading very slowly. Let's try one more with this. So looking at American football, we've got a fullback and a linebacker. They're going to collide with each other. So if we've got the fullback, it's the guy with the football here, traveling to the right, he's got 120 newton seconds going in this direction. Then you've got the linebacker coming in the other direction. He's got 110 newton seconds. If they stick together, we want to know what is their momentum before and what is their momentum after. And we're looking at total momentum. So if I wanted to figure out total momentum, I just add these two up. So momentum total initial is going to equal 120 plus negative 110. So 10 newton seconds total. Why is 110 newton seconds negative? Opposite direction. So it's moving to the left. Here, momentum T for total, I for initial. If I look at total momentum final, any guesses what this is going to be? Is it going to be negative 10 or positive 10? Positive 10.
Yes, because we're going this way. And if we're going to
Yeah. So let's think about this logically, because there's no equation that I've given you yet to solve this. If this guy has momentum than this guy, he's going to push more this way. It's the same thing if you are going to tackle your younger sibling just for fun. You're going to have more momentum than them running at you, so you're going to plow them over. It's often why the older sibling gets into more trouble than the younger sibling. So whatever that situation is, notice we've got momentum total initial is equal to total momentum final. That's conservation of momentum. Whatever your initial momentum is, that's equal to the final momentum. So all those thought experiments just to get us to this. So in an isolated system, we're always going to be dealing with isolated system. Total momentum before is going to equal total momentum final. Here we go. And assuming we have two objects, this is going to be our overall equation. So momentum 1 initial plus momentum 2 initial is equal to momentum 1 final plus momentum 2 final. So this is the equation that you've got on your formula sheet. Now this can adjust depending on the situation, if objects stick together or if they don't stick together. We'll show you some examples of each of those. But you'll be using this exclusively. So let me check if there's one more thing. Yeah. So like I said, isolated system, we're going to be using those. We've got no unbalanced forces going to be dealt with. So no friction is going to be in this case. You're not going to lose energy like we did in the last unit. We're just going to deal with conserved or isolated systems. Give you a sec to write that down. So this should look very similar to what you saw with conservation of energy. Conservation of energy was the exact same thing. Initial energy equals final energy. Except now we're going to do initial momentum. So you add all the momentum of the initially, add all the momentum final, they'll equal each other. So I'm going to oversimplify a definition for the rest of this unit. I'm going to adjust it next year if you take it with me. But we're going to simplify when objects don't stick together. This is what's called inelastic. Is this the same question you have in your notes? It should be written right in front of you. So I'm going to say when objects don't stick, we're going to call this, sorry, this one's elastic. So if two objects hit each other and bounce off, elastic. In the row beneath that, I've got where objects stick together. This one is inelastic. So when two objects stick together, it's inelastic. And then the last type we're going to deal with is explosion. So these are the three types of collisions you can see. Elastic, inelastic, explosion. So I'm going to show you guys one example of each, and then I'm going to stop. I'll cover the last three examples with the group tomorrow. This one is not in the notes. What question? Okay. This is the one you have, the bowling ball question?
Yes.
Okay.
The bullet question is inelastic.
Okay.
Not the same number.
All right, here we go. This is the question you've got. So we've got a bowling ball rolling to the right. It hits a stationary bowling pin. We tell you after the collision, the bowling ball is traveling to the right. We want to know how fast the pin is moving. So often with these questions, what's going to help to make sure you don't put any wrong negatives in there is to draw out what's happening. So if I look at our initial situation, what do I have? Bowling ball. It's rolling to the right. Yeah, so V1 initial, 3.8. We have mass 1. We know that. It's the bowling ball, so 7.1. And what's our bowling pin doing? What's the bowling pin doing in this situation? Standing still. So here's our poorly drawn bowling pin. And it's standing still. So V2 initial equals 0. And M2, 0.4. Adam, is there a problem? Yes, it's never you. If it's Sandra, then move somewhere else. Mohammed, do not get involved with this. Otherwise, you'll get in more trouble than they do. So this is what's happening initially. What are we told about the final situation? Adam, come sit up here. I don't want to deal with this more. Thank you. Do this quietly so you're not disrupting my video more. Okay, so after the collision, the bowling ball is still moving to the right. So V1 final, 2.9 meters per second. What's happening to our bowling pin? It's moving. Is it moving to the right or to the left? Would it make sense for a bowling ball to hit something and then this one keeps going and this goes backwards? In your words, Yusuf, maybe. In most people's normal... So, have you ever gone bowling before? When you bowl the ball at the pins, do the pins come flying back at you? Yeah. Well, it depends on if it hits on the side or on the front of it. But in all likelihood, it's going to go this way. The nice thing about this, so this is what we're looking for. The nice thing is, if we guess the direction wrong, my answer is going to come out negative. Which just means we guessed wrong. Because sometimes you don't know. So now we've got everything we need to solve this. Nice thing is, I don't even need to look at the question. We know momentum initial equals momentum final. So we got m1v1i plus m2v2i is m1v1f plus m2v2f. Momentum of the two objects initially equals the momentum of the two objects final. Any questions with the setup so far? Okay. V2i is 0. So I can just cancel that one out. And the rest I can solve for. So the math in this is going to be a lot easier. There's no square roots. Just anything more complicated than that. It's just these numbers. So start plugging in and solving. 7.1 times the initial velocity of the bowling ball. This is going to equal m1, 7.1, times v1f. We're told that is 2.9. Plus mass 2, which is 0.4, times v2f. So here you should just be able to calculate that. $16. Any questions with this? So notice in this case, I did not put direction. Would you need to put direction in your answer? So what does it ask us for in this case? It just says how fast. Is how fast a speed or a velocity? It's a speed. So in this case, you don't have to put direction. If it said, what's the velocity of the pin? Do I need to put the direction? Well, it depends. So yes, I need to somehow see that you put direction. The thing is, here I showed what direction I'm going. So if you draw the diagram, you've already given me direction, and that's fine. If you do not draw the diagram, your answer should have a direction. But that's if it's asking for velocity. Any questions with that? The process? Okay. So notice here, two objects hit, and they bounce apart. This is the first type of collision. Let's look at inelastic. So here we've got a hockey puck that is caught by a goalie. We want to know what the velocity of the goalie will be after catching the puck. So can you see how, in this case, the two objects stick together? The puck is coming this way, the goalie catches it and holds onto it. So let's draw this out. Here we've got our hockey puck. it is moving this way. So we've got V1 initial is going to be 48. So notice, when I'm setting this up, look at all the information I'm writing down. This is just really helpful for you to be able to organize your thoughts so that you can be able to put this in your answer a lot easier. Do you have to write this out? No, you don't always have to write it out. But this is great for getting part marks. So here's the puck. It's going towards our goalie. So here's our, the goalie here's standing in the net. Yes, I know I'm doing great at drawing. And then this is V2 initial is 0. We're at rest. And we have mass 2 is 75. Good with that? If you don't want to show off your artistic drawing, you can do everything as a box. That's totally fine. So finally, here's our goalie. He's got the puck in his hand. And he's moving backwards at some velocity. So here we've got V total final. And we're doing a total because now these two objects are stuck together. So not only do I want the V total final, but I need to figure out what is the mass total, because I'm going to treat this as one object now. And to do that, I just go M1 plus M2. So 75.105 kilograms. So when two objects hit and they stick, this is going to be the what I need to deal with. I need to deal with it as a total system. So now getting into momentum. Momentum initial is equal to momentum final. M1V1I plus M2V2I. And here's where the equation now changes. It's now M total, V total final. So again, this is not going to be on your formula sheet. Because you don't need it. How do you know that I'm going to have mass total, V total final? If they stick together. So based on the question, you'll be able to figure this out. Yeah? I added the two masses together. 75? Because they're stuck together. Because they're stuck together. If the goalie catches the puck, they're now one object. So does this number make sense? I've got a really tiny number. Should I have a really tiny number? No. Why are you saying no? Because I said it in a weird way, so therefore it must be wrong? No. 75 should be in kilograms.
75. He said, no, 70.
Okay, you just want to repeat what he's saying?
No, yeah, I thought he did.
No.
It's like,
Well, let's think about this. Have any of you ever watched a hockey game?
no.
No, you've never watched a hockey game? Have you ever watched a football match?
Yeah.
Okay. So, would you say that a football is heavier or lighter than a hockey puck? Football is going to be slightly, they'll be around the same, I think. They're a bit bigger but filled with air. Have you ever seen a goalie in a football match try and stop a kick and they fly backwards? Do they fly backwards? I don't know what kind of football you watch, Omar. So, would it make sense that if you catch an object that is very light compared to you, that you go flying backwards? It makes no sense. If the goalie would fly back fast, that means they're going to go into the net. So you're going to have to kick that ball really hard or hit the hockey puck really hard for that to happen. So we've got a really tiny object moving at some speed. It's not going to move the really big object. There's not enough momentum to push it all that far back. So this number does make sense. So Abdu, just because I say something funny doesn't mean it's wrong. It means it's a teaching point. I don't know what's going on with this class today. You're not sorry, because you keep doing the same thing that I tell you not to do. You do not. Fasting, lack of sleep. Yet there are individuals who can do it just fine. Mohammed, I completely agree with you. So even though others are laughing, I completely agree with you. So, do you know English 100%, Abdu? No. So don't make fun of someone else just because they mispronounce something or they pronounce it different than you. There are many different variations on different English words that I hear throughout the day. You don't hear me laughing at everyone who makes a different mistake. So, here's our last one, an explosion. So we've already seen elastic, two objects that hit and bounce off each other. We've seen inelastic, two objects that hit and stick. Last one's explosion. They start together, then come apart. These are your three types of collisions. So let's give this one a try. Same thing, we're going to draw this out. Let's draw our really fancy gun here with the bullet inside. Initially, they're like this. Notice here, I'm dealing with V total initial because they're stuck together. This is 0. Not told anything. We're going to deal with mass total again because they're one object. So add these two things together. It's 5.05. And finally, here's our gun. It's going to go backwards. Here's the bullet. It's going to go forwards. So you are told, let's say this is V2. Final is 275 meters per second. And we're looking for what is V1. Good with this? You understand what's happening? Yep. What's the recoil velocity? Recoil just means when you shoot a gun, it backfires. So in this case, because we've got an explosion, still momentum initial equals momentum final. That's not going to change. This is worth a mark, by the way. If you just simply put this on a conservation of momentum problem, then you're good. So M total, V total initial, goes M1 V1 F plus M2 V2 F. Hopefully I haven't lost anyone yet. Total initial velocity, 0. So it's at rest. So therefore, plug in all the numbers and solve it. So 0 equals, what did we say is the first one? The gun. So 5 V1F is what we're looking for. Plus M2, which is the bullet, 0.05. And it's going 275. Notice my velocity is negative. Does that make sense that it's negative?
No.
Yeah, it does. Again, thinking about this physically. Those of you who have shot a gun, when you shoot a gun, does the gun go with the bullet?
No.
It goes backwards. So it makes sense. It should be negative, it should go backwards, which is what we expected when we drew this out. So we're good. Good with that? Okay, so that is the entirety of conservation of momentum. Like I said, I'm going to cover the last 3 examples in class tomorrow. So if you're still confused about this and want some more examples, you can watch the video from tomorrow to be able to get those last ones. But you don't have to if it makes sense.